So this is where we're going to be calculating equivalence points. So it's one of the big calculations that we have to do in this unit. We're going to briefly just mention that indicators are usually an equilibrium, basically, that's set up between its indicators are essentially weak acids or bases, and which the specialty about indicators is that its weak acid and its conjugate base are different colors in solution. So therefore, when you have an acidic or basic medium, or wherever this equilibrium lies, or whichever pH this equilibrium switches at, that's going to be the endpoint which this indicator predicts. For example, phenolphthalein goes from colorless to pink at about pH 8 point something, and therefore if you have an equivalence point at around that pH, you would use phenolphthalein, because that's where the color switch essentially happens. And different indicators have different endpoints, and so therefore you would, depending on which titration or what titration you're doing, you would use an appropriate pH. So that's that for pH. For indicators, we're not going to focus too much on that, but we are going to do the homework questions on page, where are we? Yes, these guys, page 428. So, question number 5 is just practice for a salt equation, so we're just going to do that on here. If we have 0.02 moles per liter sodium fluoride, 0.02 molar. Again, we can kind of break this apart into the sodium ions, which are not going to react with water, right? Because again, you're trying to form, if they do react with water, you would form its conjugate base, NaOH, which cannot be part of the products because the equilibrium lies all the way to the ion side. So this is basically, we're going to cancel it out. And then its other side is F minus plus water, giving you HF plus OH minus. Right? F minus is a weak base in water. And here, this is possible because HF is a possible product. So this will be an equilibrium that is kind of set up in the solution, albeit, again, this lies heavily towards the reactants, but not as much as the Na plus equilibrium. So here we have a 0.02 concentration, 0.00 minus X. Okay, I just cancel out the water. Plus X, 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 0.02 minus X. So this is our ice table, basically, that we're drawing. And now we have to do two things. First things first, we have to find the Kb of F minus. So I'm going to look at the back of my textbook. So where is my... hydrofluoric acid, HF, is given to have a Ka of 6.3 times 10 to the power of negative 4. And therefore, to calculate the Kb of F minus, we know that we have to do Kw divided by Ka. And if we do that calculation, 1 times 10 to the power of negative 14 divided by 6.3 times 10 to the power of negative 4, we're going to get the Kb, because, again, this is a conjugate acid-base pair, and so the Ka of this times the Kb of this is going to equal the Kw, so we can just rearrange to solve for that. And now that I've grabbed my calculator, we can continue. So the Kb was found to be 1.587 times 10 to the power of negative 11. And now we do two things. We first do 0.02 divided by this Kb, 1.5 times 10 to the power of negative, whatever. Big number, greater than 500, justified. And then, since we canceled out this negative x, this becomes a very easy calculation. We just do 1.587 times 10 to the power of negative 11, or the Kb, equals to x squared divided by 0.02. So we're just going to multiply this by 0.02, take the square root of that, and we get our x which is our OH minus concentration, essentially, that's what we're looking for, is 5.63 times 10 to the power of negative 7. We take the negative log of this answer to get our POH, 6.25, and then pH would be calculated by doing 14 minus this answer, so 7.75. Again, if you want to do sig figs here, we had 3 sig figs, did we? We had only 2 sig figs, so that's 2 decimal places on the pH scale, so that's the answer. Okay, so this is interesting. Question number 6 is a sodium hydroxide hydrochloric acid titration, and this is again not really one that it's not really new, so we're gonna quickly run through this. Basically, I seem to have 20 milliliters of 0.1 and 30 milliliters of 0.1, and it's important to note that this is going to be in a 1-to-1 ratio. NaOH plus HCl gives NaCl plus H2O. No stoichiometric difficulties over here. Basically, what I'm going to do is I'm going to set up my number of moles. So, go away. Go away. I don't have space to do this. I'm going to do this down here. I'm going to do 7 and 8 on a different page so that we have room. But once I have, NaOH, number of moles of NaOH is going to be, 0.1 times 20, well, divided by 1,000 because of you have to convert. So 2 times 10 to the power of negative 3 moles. Right, plus HCl, which is going to have 3 times 10 to the power of negative 3 moles. And basically, these are going to react and going to leave me with excess of 1 times 10 to the power of negative 3 moles of HCl. So hopefully we can see how that happened. They reacted in a 1-to-1 ratio to, like, let's say, like 2, just ignore the 10 to the negative 3. We're just going to say 2 moles of NaOH and 3 moles of HCl. 2 of these reacted with 2 of these, and they neutralized each other, and which left me with excess of 1 times 10 to the power of negative 3 moles of HCl. Now to find my concentration of HCl, I'm going to do number of moles divided by volume of solution, 1 times 10 to the power of negative 3 moles. What is my volume of solution? It's 20 plus 30, 50 milliliters. So 50 divided by 0.05. And then we do 1 times 10 to the power of negative 3 divided by that, which gives us 0.02 moles per liter. That is my concentration of HCl. And therefore, that is also my concentration of H+, because it is a strong acid. Completely dissociates. My concentration of acid equals concentration of H+. So I do negative log of this guy here, and I get a pH of 1.699, and therefore that is the correct pH. Okay. We're going to try question number 7. Although question number 7 looks complicated. Okay, question number 7 is actually pretty complicated. We're going to do question number 8 first to get an understanding of how to do these things, and then go back to question 7, because as far as I can see, question 7 requires a bit of understanding as to how this works. So we're going to write hydrobromic acid, aqueous ammonia. So we're going to write the neutralization reaction first. Aqueous ammonia is reacting with hydrobromic acid in a neutralization reaction, so this is essentially a complete reaction. And that's going to be NH4Br. And again, these are aqueous, right? So there's water there's water in the solution, but we don't necessarily have to write that. Let's see, 50 milliliters is 0.1 mole per liter hydrobromic acid. 0.1 mole per liter. Alright, let's write that in the same. Ammonia. So the key here is we are determining the pH at equivalence point. Equivalence point is where number of moles of acid equals number of moles of base. And therefore, we can kind of automatically figure out that this volume of ammonia also has to be 50 milliliters. Okay, sorry, the app closed or whatever. Technical difficulties, let's say. But we're going to continue right where we left off. NH3 plus HBr gives us NH4Br. We have a given volume and concentration of our strong acid. We do not have a volume and concentration of our weak base. We only have a concentration. But at equivalence point, we know the number of moles of this guy equals number of moles of acid. Number of moles of acid equals number of moles of base. And therefore, we can kind of do our C1V1 equals C2V2, because if you do number of moles as concentration times volume. So if the number of moles are equal, concentration times volume of both of these are equal, right? So concentration of acid times volume of acid equals concentration of base times volume of base. 0.1 times 0.05 equals 0.1 times volume of base, which we have to find. And you can kind of see here that this is also 0.05 liters because, you know, you could do the calculation if you want, but essentially it's the same thing. Now we our number of moles. What are actually our number of moles? So number of moles are this times that, which is 0.005 moles. And this should be the same for both the acid and the base, because if it's not the same, then it's not at equivalence. So it has to be the same. And you think, so if like 5 particles of this combine with 5 particles of this, they will give you like 5 particles of this, because you're just putting them together, right? And this is always the case. So because we're going in a 1-to-1-to-1 ratio, there's no limiting reagent per se. Both of these are limiting reagents at equivalence point, and you will get 0.005 moles of NH4Br. You can do that little chart if you want to, taking either of them, because both of them are limiting reagents. So 0.005 moles NH3, for example, then chart 1 mole NH4Br, 1 mole NH3, and you know, that's just 0.005 moles NH4Br. Right, and now to set up in our ice table, we need concentration of NH4Br, which is going to be number of moles divided by volume, which is 0.005 moles, divided by, again, from here, you can't really do that calculation, or can you? I think you could. I'm not sure how to do it on a table, but total volume would be 0.05 plus 0.05, which is 0.1 liters, right? Because you're adding 50 milliliters of this solution, 50 milliliters of this solution, so finally in your beaker you will have 100 milliliters of that solution. So if you divide that by 0.1, you get 0.05 moles. Am I doing this right? I think so. Well, not moles, but molar. Yeah, okay. So you get that concentration, and then you can, again, you kind of have to, you can do this in your head, you don't really have to show it to me. You have to know that the Br minus does not really react with water, because HBr is not a weak acid, and the reaction lies very, very, very heavily to the left, so that's a no reaction almost. But NH4 plus, I mean, this is going to split the salt into its ions, NH4 plus and Br minus, does react with water in a substantial quantity to give me ammonia and water. So I start with 0.05, water's gone, 0 minus x, 0.0. And this is exactly continuing where we left off in question 1. I know the Ka of ammonia, that's bad, from the back of the textbook is, let me see, ammonia, 1.8 times 10 to the power of negative 5. And so Kb of ammonium is going to be Kw divided by that Ka of ammonia. So 1 times 10 to the power of negative 14 divided by 1.8 times 10 to the power of negative 5, which is equal to 5.5 bar times 10 to the power of negative 10. I can do my small x justification, 0.05 divided by Kb greater than 500, therefore justified. And therefore I can just, next step, set up 5.55 times 10 to the power of negative 10 equals x squared divided by 0.05. Multiply Kb times 0.05, take the square root of that, and I get x equals H3O plus concentration equals 5.27 times 10 to the power of negative 6. I'll take the negative log of that answer to obtain my pH, which is, interestingly, also 5.278. Wow, never seen that happen before. It's interesting because 5.27 is 2.78, and then negative 6 was fascinating. Very cool. But that is how you calculate the pH of a titration question. Essentially, we're going to break it down. We have to find number of moles of the salt, which is always equal to the number of moles of the acid and the base, because it's at equivalence always. So there's no, you just find either one and you calculate that. Technically, the reason we had to do this little thing to calculate the volume was because we needed the volume for our second step, which is basically calculating the concentration from the number of moles. So we needed the total volume, and so we needed to find the volume of this guy added. We calculated our concentration. Then you set up an ice table for a salt. And the only difference between an ice table for a salt and an ice table for an acid is for a salt you have to do this extra Kb calculation to obtain the K value that you use in your calculations in your ice table, and that's it. So again, not that super difficult, hopefully, but well, more or less. There you go. Okay, next question is kind of based on similar patterns, but is kind of confusing-ish. 0.025 mole per liter benzoic acid titrated with 0.025 mole per liter sodium hydroxide. Notice that I'm not given any volumes here, so we kind of have to do some, I'm going to say C6H5COH plus what acid was it? Sodium hydroxide 0.025. And now I know I'm going to get my basic salt here, CO minus Na plus. You can split it into its ions, sort of, or you can not split it into its ions. It doesn't really matter. Now again, interestingly, I'm not given any volumes, so I have to calculate the total concentration of this. But I know that these two things have essentially equal concentrations. So at equivalence point, which hopefully is mentioned, at equivalence point, they will have equal volumes as well, because again, number of moles of this has to equal number of moles of this. No. Sorry again, I think my computer is too full of space. So, okay, so number of moles of this equals number of moles of that, and therefore the volumes will also be equal to each other. Again, you can kind of say, okay, let's say the volume is like some quantity L. Is that L liters? Is that too confusing? Let's say I do V liters. Maybe that will help. Oops. 0.025. Let's say V liters here and V liters here, but you know that they're equal to each other, basically. And therefore, when we set up this equation, I will have a number of moles you can calculate as concentration times volume, 0.025 times V. This is also 0.025 times V, whatever that V is. And so I will get 0.025 V moles, even for my salt here, because again, it's a 1:1:1 ratio where both of these are simultaneous limiting reagents because they have the equal number of moles, right? And now here, now that I have my moles, I'm going to find concentration of C6H5COO by doing number of moles divided by volume, 0.025 V. Now the volume here would be 2V because I have to do V plus V, essentially, because my total volume is double whatever original volume I had. It doesn't really matter what original volume I had because I have doubled the volume. So I can cancel out the V's, and so my concentration will basically become half of the initial concentration. Right, so that's why this was a bit trickier to process, but that's okay. We figured it out. And now, hopefully we can skip the process where we say Na plus is not going to react in water because it's a conjugate of a super strong base, and therefore we can ignore it because the equilibrium will lie far towards the ion side. What does this give me? OH minus. We have 0.0125, 0 minus X. And to cancel out this negative X, I had to do my 0.0125 divided by Kb is greater than 500, which I know it will because I have just calculated my Kb from, again, the Ka of acetic acid. Ka of acetic acid is 1.8 times 10 to the power negative 5. So Kb of acetate is going to be Kw divided by the Ka of the conjugate, which we've done just before, 5.5 bar times 10 to the power negative 10. I think, is that what we got up here? Yes, that's what we got up there. So come back down, and we just say that this is justified because I do that, and obviously it's greater than 500. Again, 5.5 times 10 to the power of negative 10 equals X squared divided by 0.0125. So I do 5. Take the square root of that answer. I get X equal to OH minus equal to 2.63 times 10 to the power of negative 6. I take negative log of that answer to give me my POH, which is 5.58. And then my pH is essentially 14 minus this answer, which gives me 8.4. And I expect that to be basic because I have a titration between a, as we see here, a strong base and a weak acid, which means my solution, which my salt, will basically be basic at the end. Therefore, we know that that seems correct, and therefore that is our equilibrium point calculation questions. I'll be doing one more as part of the review video, so you can look into that as well if you have more questions or need more practice there. You can try the ones that we did in class again, or that I posted. There's one question in the review that you can do. So, all right, see everybody in class.